So we're now ready to start transitioning to coverage of Java parallel streams. Now that you know a fair amount about Java sequential streams, you'll discover that there's quite a bit of overlap. And so I'm going to spend some time here talking about what a parallel stream is at a high level, and then we're going to kind of dive down and look at how it behaves under the hood, which will give you some better insights about when and when not to apply parallel streams. So basically, a Java stream, as we know, is a pipeline of aggregate operations that process a sequence of elements or objects or values or data, whatever you want to call them. And this is kind of a classic Java stream. If you take a look at this link, it's the search stream gang link, you'll see this example. It's very similar to the simple search stream program we looked at before. And what it does is it takes the complete works of Shakespeare, all 37 plays and then his sonnets, and a bunch of phrases, and it goes and it searches through the works of Shakespeare to find whether there's any matching phrases. So it's kind of a generalization of the earlier example we looked at, which just had a single input, which was the lyrics for the Do Re Mi song, and we were looking at words from that song. So very similar kind of idea. In this particular context, you can see that we start out with, say, a list, which is the list of strings, which would be the input. And in the sequential version, what will happen is that everything will run in one thread. The stream will take each of the works of Shakespeare, and then it'll go search for phrases in each of the works of Shakespeare. If it finds a match, then it returns a search results object that has something more than 0 elements in it. If it doesn't find a match, it'll return a search results object that has a value of 0 or it has nothing in it. So then we use the filter intermediate operation to get rid of things that have 0 elements in them, search results with 0 elements, and then we collect the results up into a list. So that's basically how it works. And the aggregate operations, which are the things that I've colored in red here, all use internal iteration and the behaviors that are passed in here in order to process elements in the stream. So that's kind of the sequential version. And in the sequential version, surprise, surprise, when you use the .stream factory method, then everything runs in one and only one thread of control. But we can do better than that, and we can trivially do better than that. So what we have to do, and what you'll need to do for your programming assignment 1B, is put parallel stream or something equivalent to it in a couple of places in your code, and boom, all of a sudden things are running in parallel, taking advantage of multiple cores on your underlying hardware and your virtual machine and operating system that supports multi-threading. And what happens, this is just a little cutaway of it, but if you really want to know what's going on under the hood, the work that's being done is being done basically, as we talked about before, it's being done on a top to bottom, left to right style. And what'll happen is that threads that are in the common fork join pool, which we'll talk about more later, will process different chunks of data. And literally the way it works is that the different chunks, which in this case would be vertical slices going through the various intermediate operations, will be run in a pool of threads. And so in steady state, you'll have all the threads in the pool busy doing computations on these slices, these vertical slices of the data. And that often leads to big scale up as long as you know what you're doing. And as long as you strive to use stateless, pure functions or behaviors as much as you possibly can. And as I say here, the intermediate operations cleverly process the behaviors on these chunks in parallel, and it's clever because it does it in these slices, these vertical slices, as opposed to horizontally. If we did it horizontally, two things would be problematic. Number one, doing short circuit operations would be problematic because a lot of extra work would be done. And number two, we'd end up with a lot of overhead moving things between different layers. And the way it's done here, we do it with what's called integrated layer processing, where all the operations are done in a given thread, which works better with caching and other things that are sometimes hard to reason about abstractly, but make a big difference in the actual performance on real hardware. The terminal operation, of course, is what sets everything in motion. When we describe this stuff, we often make it sound as though these phases get done first, but in reality, it's only when collect is hit that things run. And the reason for that is that the way that streams work is it's actually, these calls here are actually building a linked list at runtime or a pipeline at runtime, And it's not until we see the final element, which is the terminal operation, that everything in that linked list starts to work. So it's really quite clever and very cool, and we'll talk about some of the internals in a bit. Now, one of the most important things to remember, and we'll talk a lot about this because failing to do this will lead to chaos and insanity, is we want to have behaviors that are stateless, typically method references and/or lambda expressions. If you don't have stateless stuff, then bad things will happen, or slowdowns will happen. And we'll talk a bit more about that when we talk about some of the hazards of parallel streams programming. And ideally, and again, you will get a very firsthand appreciation for this, ideally, converting from sequential to parallel streams should require just minuscule changes. Hardly anything needs to be done. And that's really the whole point of assignment 1B, is just to see that. And then, of course, what's cool about assignment 1B is once you get it up and running, you can run it in your emulator or on your device, if you have a device that's using the right version of Android, mobile device. And what you'll see, literally you'll see it's different. You'll see the behavior when it runs is not the same as it appears when it's sequential. When it's sequential, it'll do each of the different images downloaded, transformed, and stored kind of one at a time in very nice sequential order from left to right, top to bottom. When you do it in parallel, you see a big burst of these things occurring, especially if you have a multi-core processor, or if you have a multi-core processor, which everybody probably does. You'll see bursts of things happening. So it literally looks different. And that's one of the reasons why we have that cool GUI, so you can get a better appreciation of how it all works and you can visualize it. OK, so another thing that's important to remember here, the same operations, map, filter, collect, and so on, reduce, they can be used for both sequential and parallel streams. It's really apples to apples. You don't have to change the programming model drastically when you move from one approach to the other, which is, again, part of the virtue of all this stuff. So there's this example that we talked about, the search stream gang. It's got about a dozen different ways of doing the implementations. For the moment, we're just going to talk briefly about the sequential version and the parallel version. And if you look at the implementations, they look almost identical. And they have the same intermediate operations. They have the same terminal operations. And the only difference is it's stream versus parallel stream. So that's a nice warm, fuzzy commonality that you can leverage. If you do take some time to look at this example, there's lots of other ways of doing this stuff. And it's kind of fun to see how they work and see how they perform. The whole thing is benchmarked in a clever way, so you can do an apples-to-apples comparison of performance of different approaches. We'll talk about some of those things later. So basically, Java streams can treat parallelism as an optimization, and they can take full advantage of all the cores that are available on the platform if that's what you want. Now, you can also limit stuff if you're clever and play some other tricks. And there's other things you can do as well that we'll talk about later. But the good news is, without a lot of work on your part, you can take advantage of multi-core processors. And remember, that's the big motivation for all this stuff in the first place, was to make it easier for mere mortals like us to take advantage of all the parallelism that's available on modern multi-core platforms. Always remember, of course, that the behaviors that are run by these aggregate operations need to be carefully designed to avoid accessing or manipulating unsynchronized shared immutable state. That is the root of all evil in concurrent and parallel programs. So the way things work is that the data is partitioned cleverly by different phases in the stream, particularly the split iterator part. The split iterator breaks everything up into these little chunks, and then those all run in parallel on different parts of the data. And so as long as you're smart, never the twain shall meet, so you can quickly get embarrassingly parallel solutions that scale very nicely. The easiest way to avoid problems with shared mutable data or shared mutable state is to use stateless behaviors, where everything is self-contained. So they don't have side effects, they're lightweight, and you aren't sharing anything. Now, that's sometimes easier said than done, and we'll see some examples where you have to be a little careful, and we'll talk later about ways to overcome this. In fact, I think the very next lesson, or an upcoming lesson, will talk about that. So that's a quick overview of parallelism and Java parallel streams. Even though we didn't dive much into the details, you actually know about enough now to do assignment 1B, because it's so easy to convert from sequential to parallel streams.